Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. In the last lecture, we began our discussion of quantum systems. So, the interesting thing about quantum system, apart from the applications and the usefulness in modern information processing, quantum systems also offer the possibility of quantum phase transitions driven by quantum fluctuations at zero temperature. So, we started with the simplest quantum system, which is a qubit in a transverse field H, which we showed had a Ising symmetry, and this is a quantum zero-dimensional system. The qubit we found has an analytical free energy, and what this means is that there are no phase transitions associated with any nice values of these parameters t and h. We reinterpreted the partition function of the qubit as a sum of amplitudes over propagation in imaginary time, and we were able to make a very interesting connection that the partition function of the quantum qubit, zero-dimensional quantum qubit at a coupling constant beta h was equivalent to the classical partition function or partition function of a classical Ising model with n tau sites, where the temperature or the inverse temperature of the quantum bit was n tau times delta tau, and the coupling constant k of the classical system was related to the quantum problem by this expression. From this, we were able to make a very interesting connection that when I let n tau go to infinity, that is when I take the classical Ising model to its thermodynamic limit, I am looking at the ground state, namely the zero temperature state of the qubit. So this gave us an insight as to why at a finite k, at a finite coupling constant, the classical Ising model does not have any non-analyticity or phase transitions, because the associated quantum problem is at zero temperature with a unique ground state. And this is a fairly interesting and intriguing insight. So what we will do in this lecture is we have seen the physics of a single qubit. Now you can ask, what happens if I let this qubit be on a chain and let them interact with each other? So I'm going to introduce a model today, which is a very, very famous model in physics. It is called as the quantum Ising model, or many people also call it the transverse field Ising model. Okay. So let's build the transverse field Ising model from scratch, so to speak. So imagine that you have a bag of qubits and you prepare a lattice. So I start from I equal to 0 and go all the way to I equal to n minus 1, and then I put periodic boundary conditions. So the site n is same as site 0. This is our usual convention. So from your bag of qubits, you pick one qubit and place it at this site and place another qubit at this site and so on. And so what I have is, at every one of these sites, I have if you like, a local vector space Vi, which is a two-dimensional qubit space at site I. And this, using the notation of our previous lecture, is spanned by the Z operators associated with the qubit Hilbert space at site I. So I have done this on a one-dimensional chain, but you can certainly generalize this model to any dimension. You can put some cubic lattice, you can put any lattice actually, right? And we will not discuss the d-dimensional case here. We will focus on the one-dimensional case. So I place a qubit at each site, And the qubit Hilbert space, like I said, is spanned by the up state and the down state. The next question actually to ask is, what is the state of this full system? How do I understand the state of this full system? So for this, we have to use a mathematical concept as of the tensor product. But before I do that, I have to also mention that at each of these sites, there are these Pauli operators associated with the Hilbert space of the site I. So these are, for example, the Pauli operators associated with the Hilbert space located at the site that I'm pointing to. And again, these SIs are eigenstates of the Zi operator. Okay, so how do I construct the Hilbert space of the chain? So for this, I need the notion of what is called as a tensor product. So the statement is that the Hilbert space of the full chain is the tensor product Hilbert space of each of these individual Hilbert spaces. Okay, so how do I get a basis of this? So what you do is you take basis elements from each of these local Hilbert spaces I, so they can be labeled by Si, so Si can be plus and minus 1, and you tensor all of them. So this state is labeled by a set of SIs, the values of the plus or minus 1 you have chosen at each site, and you will see that this state, which is a tensor product of these Si states at each site I, form a basis. In fact, you can show that any Si is orthogonal to any other Si where these entries are different. Even one is different, they are orthogonal. And you can see that the dimension of the Hilbert space is 2 power n. And this should be reminiscent of what we did in the classical Ising model. The important thing is that although there are 2 power n basis states, I can complex combine any of these 2 power n states in many bazillion different ways and get very different states, which is not possible in the classical system. So this is what I am stating here, that a generic state is a complex linear combination of all these basis states, and associated with each basis state there is some complex number, and that basis state is actually given by a set of spin values on each SI values on each site I, and this is what we mean by a general state of the quantum system that we have shown in this picture. Now we will not have time to discuss this in great detail, but such a state, a general state, can be entangled, which means that this state cannot be written as a tensor product of local states. So if a state cannot be written in this fashion, then it's entangled. Okay? All right. So now we have seen the kinematics. How do we describe the states of our system? Now remember that when we chose degrees of freedom, we will choose degrees of freedom that will allow us to implement some kind of symmetry. So the symmetry that I would like to implement here is an Ising-like symmetry. That means I must have some symmetry operation which will square to 1. Okay? So for this, I am going to define what are called as global flip operators. So there is an operator F, which is the tensor product of all the Pauli X operators at each site. So you can check yourself very easily that the action of the flip operator on a basis state, F acting on the state given by Si, will take it to the state with opposite stuff. So for example, if I take a fully polarized state up, which is tensor of Si equal to plus 1 at every site, up state, that will be changed to the fully polarized down state. And similarly, the flip on the fully polarized down state will take me to the fully polarized up state. And now you can see immediately that this will square to 1. Okay. Okay. So in our discussion, as we proceed, we will also need another very important state. And so that is shown by this double right arrow. So what is this state? So first we look at a local Hilbert space located at I, and ask what are the eigenstates of the Pauli operator X at that site. So those are the what we call X polarized, and hence we show it by an arrow along the X positive X axis. So you will see that this state which is pointing right in the X axis has a +1 eigenvalue, and the one with pointing left at I has a negative eigenvalue. And you can say that the one pointing right is 1 by square root 2, the plus linear combination of the up polarized and down polarized state. These were the states that we used in our basis. So if you're not familiar with this, or if you need to recall this quickly, you should pause the video and quickly work these things out, because these ideas will get used repeatedly as we go along. Okay, continuing on, you can define this fully right polarized state, X plus polarized state, as the tensor product of all the right polarized state at site I and the fully left polarized as this one. Now here is a very interesting result. So when flip acts on the right polarized state, it will give you back the right polarized state, which means flip is invariant under the right polarized state is invariant under the flip symmetry. So if I put a quantum state in this, if I put my system in this state, it will be flip invariant. Now F acting on the left polarized state will give you -1 to the power number of sites in the system times left polarized state. Now you might think that this is changing the state. Actually it's not, because the physics of this state is not changed by a phase that you will multiply on it. It has consequences which we will not have time to discuss in the course, but this is still invariant in the sense that you are not changing the physical state is not changing, only it's picking up a phase. So here's an interesting exercise for you to make sure that you have understood all of this, is you can ask, I defined a generic state in the previous slide, what is the action of F on a generic state? Okay. Okay, for the purpose of completeness, we also need to discuss the identity operator on the Hilbert space of our full system, and that is simply the tensor product of identity operators coming from each of the qubits. It's a very natural definition. Okay, and you can show that this, when you square the F, it will turn out to be this identity operator. That's just following trivially. Okay, so you can again make sure that you get all this by working it out. Okay, so what we have done is we have introduced the kinematics by introducing a Hilbert space. We have introduced a symmetry operation on the Hilbert space. We know how the symmetry acts on our states. And what we would now like to do is we would like to write down a Hamiltonian which is invariant under this symmetry. So that will complete our model construction. So what I'm going to introduce is the so-called Ising ferromagnetic interaction and a transverse field. So this Ising ferromagnetic interaction simply looks at the states of the neighboring qubits, nearest neighbor qubits, quote unquote measures their z components, and if the z components are parallel, that's what this product of z I plus 1 and zi, you gain an energy J which is taken to be positive, because we are using the convention of ferromagnetism with a minus sign. So because we are choosing J positive, if the spin states, the Z component of spin states are pointing in the same direction, so to say, between I plus 1 and I, then you will gain energy. So now you can see why this is called a transverse field. So left by itself, the system will want to point in the Z direction. The qubit will want to point along the eigenstates of Z plus or minus. And the neighboring qubits will want to be in the parallel states. But this term is a transverse field. It wants to take the qubit state from the Z polarization to the X polarization. So that's what it wants to do. That's why it's called a transverse field. So this is our Ising exchange coupling, and H is the transverse field, and these are the energy scales in the problem. Now you can easily check that the Hamiltonian is flip invariant, that is FH F dagger is equal to H, and therefore we have constructed a model with Ising symmetry, and this is the Hamiltonian for that model. Okay, so these operators now, the identity and F together form what we call a representation of the Ising group on the Hilbert space of a full transverse field Ising model with n sites and periodic boundary conditions. So you may wonder what is a quantum about this. So the quantumness of this problem comes from the fact that this piece of the Hamiltonian, which is the H exchange or Hj and H transverse field, they don't commute with each other. So you can show that they don't commute with each other. And in fact, the non-commutation comes from the fact that this operator Zi plus 1 Zi does not commute with Xi. It of course also does not commute with the Xi plus 1. Okay. So this is the crux of the quantumness here. Because you don't have these terms commuting with each other, the states of the system cannot be simultaneous eigenstates of these two, because they don't have simultaneous eigenstates. So there will be give and take, and this is what will drive phase transitions. So in certain regime, these objects will produce one kind of entanglement, and the other regime will produce a different kind of entanglement. Okay, so that's the quantumness of the problem. So I hope you appreciate why this is called the quantum Ising model or the transverse field Ising model, because the transverse field doesn't commute with the Ising term of the Hamiltonian. Okay, now you can ask a question: can a quantum system, we saw single qubit doesn't break any symmetry. Can a quantum system break symmetry? So let's look at the ground state, means we're going to look at the zero temperature, and let's work in the limit where the exchange coupling is 0 and H is positive. So here what happens is only this term is operative, this is 0, and H is positive. So every qubit state, so you have n qubits that are now not talking to each other, every qubit state will point in the plus x direction. So it's the right polarized state. So you'll get a unique ground state, which is the right polarized state, and you can check by explicit computation, straightforward computation, that this is invariant and therefore it does not break a symmetry. Now let's look at the other limit. Let's turn off the transverse field and let's look at J positive. So if J is positive, what is the ground state I can get? So for example, I could construct the fully up polarized state. So that state is certainly a state with the lowest energy. But so is the state with all down. In fact, when H is equal to 0, you can linearly combine these two states by arbitrary linear combinations, complex linear combinations, and you can make sure that the magnitudes all add up to 1 and everything. Then you will find that this state also has the same energy as the fully up polarized or fully down polarized state. So what I have here, if I just naively think about it this way, is that I have a two-dimensionally degenerate ground state. Right? That's what I'm finding here. But interestingly, if I take arbitrary values of alpha up, alpha down that satisfy this condition, that's the only condition I'm imposing, you will find that this is not flip invariant. So if I hit this, then this will become, all the up polarized state will go to down polarized state, and down polarized state will go to up polarized state. So since f is a linear operator, it just walks through this alphas, and then you will get alpha up and alpha down, and in general they are not equal. They could be equal for special values of alpha, but in general this is not parallel. In particular, it's not just a phase times the original state, and therefore you actually break symmetry. But you can do better. You know this by now. You can add a symmetry breaking field HB, right? So now if I add the symmetry breaking field, it's a quantum operator that I'm adding here. Please note it. You will now see that this HB will not be invariant under the symmetry, because Z will not commute with the flip operator, and therefore you will see that this will not be invariant under the flip operation, and that's why it's called a symmetry breaking field. And now I invite you to do this calculation. You will be able to show that if you take the thermodynamic limit first and let H at H is equal to, at the transverse field equal to 0, and then let HB go to 0 plus, you will see that this will be still the fully up polarized state. And if you do that in the other limit where you have changed the exchange to 0 and the transverse field is kept non-zero, then you will see that it is a right polarized state. So you should work out these results, and you can of course characterize this by an order parameter. So what is the order parameter? So I define an operator script m, which is the average Z polarization, right? So I just measure this object, that gives me the average Z polarization, and the expectation value of this m is what I call the order parameter. And the non-zero value of m indicates a broken symmetry. And indeed, when j is greater than 0 at h is equal to 0, that means I just have the Ising model, I get 1, which is indicative of the broken symmetry. And in the other limit, where when I said j equal to 0 and when h is positive, I see that the magnetization is 0 and the system does not break symmetry. So what we have seen is that in either limits, when I have in my quantum problem, I can break symmetry or not break symmetry. Okay, so the next thing I would like to do is I would like to discuss the transverse field Ising model in thermal equilibrium. So what I'm going to do is I'm going to place the system in contact with some bath, which is at temperature T, and we know once I do that, the system is going to be described by the Gibbs density matrix, which is given by e to the minus beta h 1 by z, and z is a partition function which is trace e to the minus beta h. So if you want to go ahead and compute this, you will see that this will become a very difficult problem, actually practically impossible problem for some reasonable values of n. So what you'll have to end up doing is you'll have to find the eigenstates of the Hamiltonian, and you'll see the partition function is simply e to the minus beta sum of the eigenstates, and there are 2 to the n eigenstates because that's the basis of the Hilbert space, and this is the density matrix. So if you take n equal to 25, I think it will be impossible, even if you use all symmetries and all of that stuff. I mean on the computer. I mean analytically, of course, we'll see later what to do. Okay. Now, instead of going through the route of diagonalizing the Hamiltonian, we are going to play our game of thinking about reinterpreting the partition function as imaginary time propagation. So what I'm going to do is I'm going to run over my basis states. Remember, basis states are given by choosing up and down polarized states at each site. So there are 2 to the n possibilities, orthogonal states you can get. You run over all 2 to the n of them, and you sandwich this e to the minus beta h between this 2 set of states, the basis states. So this can again be interpreted as if I am looking at the imaginary time propagation in imaginary time beta. Okay. So I start at tau equal to 0 imaginary time, and I reach back the state, the same state at time tau equal to beta. I'm going to play the same game that I played with the qubits. I'm going to step in imaginary time. So what I'm going to do is I'm going to take beta and write it as n tau times delta tau. Okay. So what I have to do now is, this is my space, if you wish. This is the space meaning this is my lattice, this is the set of points on a lattice, and I introduce tau in the other direction, in the direction normal to this. I have introduced this as a tau direction. Okay. So there is tau going from 0 to beta, and this has been split up in steps of delta tau, and each of the time steps I'm going to label by little l going from 0 to n tau minus 1. So tau l, for example, the imaginary time at this slice here is tau l equal to l times delta tau. Okay. All right. Now I have this partition function, and I want to interpret this as an amplitude, and I'm going to step through imaginary time. So what do? I take this e to the minus beta h and slice it up into propagators associated with delta tau. So I'll get n tau, a product of n tau such operators, and each of those operators are sort of, you must imagine as these sort of orange lines that I'm showing here. Okay, links in imaginary time. Okay, now I try to do something with this thing. So what I'm going to do, between each of these e to the delta tau h, I'm introducing an identity operator at the lth time, at tau l, and I'm going to write it using the complete set of states which are the z polarized states, and for at this tau l times stamp, I can choose different combinations of plus minus ones at each of the different sites, and that is what I mean by SIL. So this is the spin state in this basis state that I am choosing at site I, at time tau l. That's what this means. Okay. So this now becomes, after introducing this partition of identity, I can write this entire thing as propagating from the state SIL at time tau l here to going to this time tau l plus 1. So that is what this is. And then I have to product over the entire set of tau steps. And so you see, so the full amplitude of propagation is products of such amplitudes. That's what I'm saying. So now I need to be able to compute this quantity. So the computation of the partition function has been reduced to computation of this matrix element, or the amplitude of propagation of a state of the many body system. Remember, this is state of the full transverse field described by this SIL at time tau l to SIL plus 1, which is the state that you will realize at time l plus 1, and this is the amplitude of that propagation. Okay, if we work on, I want to evaluate this, therefore I need the structure of this exponential e to the delta tau h. Now h had two pieces. There was the Ising piece described by J, and there was the transverse field piece. Now they don't commute with each other. Now if two operators don't commute with each other, then e to the a plus b will not be equal to e to the a times e to the b, if a and b don't commute with each other. In fact, if you have some small parameters like delta tau multiplying them, you can show that exponential of delta tau times h transverse field plus h Ising is exponential of the transverse field term and exponential of the Ising term plus something which is of the order delta tau square. So you incur an error if you truncate this and make it into, if you say that this quantity is the product, exponential of the sum is product of the exponentials, you are going to incur an error which is the order delta tau square. So you're now going to proceed by saying or insisting that you will agree to choose delta tau small, whatever that means. Okay, so in the field, this is called as Trotter error, after Trotter, who introduced these kind of ideas. Okay, now what I'm going to do, I'm going to go through a set of steps, and the steps are color coded. I'll walk you through each of these steps, and the reason for going from one line to the other, they will be also color coded and shown below. And remember, I have introduced two quantities here. Ks is delta tau times j, and k tau is minus 1/2 log tan h delta tau h. They will show up in the calculations. Just remember that they have been defined here. You can understand what they mean after a little bit. So I start from this expression. This is the exact expression we want to evaluate. I'm going to trotterize this. I'm going to say that this exponential of sum of two operators is product of the exponentials of those operators. That is an approximation, and that is why you have an approximation sign. Now I claim that this term is, you hit this operator on this state. I'm claiming that it will produce a number for you and give you back the same state. So what I'm insisting is that this state is an eigenstate of e to the delta tau hj. Okay, this follows from this fact that the z polarized states, so if I have a state, unentangled state, which is a product of z polarized state at every site, that is an eigenstate of hj. Yes, because it's just the Ising state, right? And the eigenvalue, okay, there is an error here. So this is Si plus 1L, and this will be SIL here. Okay, so there is a small error here. There's an SIL here. So that is what gives you this result. Okay. Now where is this Ks coming from? This Ks is now coming from the fact that it is delta tau h. So delta tau j will get multiplied, and that is why you get Ks. Instead of, our usual definition of K was j divided by t, but now, or beta j. Now instead of beta, you are having delta tau. That's why you call it Ks. The meaning of S subscript will become clear later. So you'll end up getting this term here. Okay. So now you see that I have this quantity, which is a matrix element now of e to the delta tau transverse field, some unentangled state with z polarizations well defined at every qubit at time L, with a similar, maybe different state at L plus 1. Okay. Now I claim that that is equal to the product over all sites, and this is the state at the qubit I at time L. So you see these curly brackets have gone, and we are now writing it as the state. Remember, this state is a tensor product of these states. So I'm undoing the tensor product, so to speak, and I'll get this state and that state. So basically what I'm using is the fact that these xi operators at different sites commute, and since this is an unentangled state, etc., I can simply take I can undo the tensor product of these and just take matrix elements over individual qubits and just product them. Okay, so that's what is written here. This follows from the fact that e to the delta tau h is this, and that is simply, okay, delta tau h xi here. Okay, and that this is set of unentangled states. Okay, but what is this quantity? So if you had listened to the previous lecture and worked out the details, you will realize that this quantity is the transfer matrix like term that we had found between these states connecting the qubit to the one-dimensional classical Ising model. So I do exactly that trick. So I rewrite this term as square root of cos delta tau h sin delta tau h e to the k tau, where k tau is now exactly this quantity. So that's e to the minus 2k is equal to tan h delta tau, that stuff. And you will see that you will get this term k times. And what is this telling you? K tau times SIL plus 1 and SIL. It is saying that there is an Ising interaction with a coupling constant K between the spin state at IL, that is at site I at time tau L, and along the time direction, you take one step up, that's what this IL plus 1, same place, same site at the next time, right? So there seems to be an Ising-like interaction between them, k tau, given by the coupling constant k tau. Okay, so this going from this step to this step comes from our study of the single qubit problem, because you see this is like a single qubit story. So what have I done here? I have shown that this matrix element here is equal to this stuff. So how did I get this n by 2 here? You see that square root, there are n sites, so I just get the same factor for each of them. And now I sum over all the sites because it's product over I, and I transfer the sum on that and I get this very nice term. Okay, so that's what I've managed to do. And this leads us to yet another astonishing result, right? So I'm going to put everything together. And so the transverse field Ising model's partition function, I had this matrix element, I went through a set of approximations, etc. I reduced this as a product from L to n tau, and I computed this matrix element which was this. Now I product this from L equal to 0 to n tau minus 1. So this factor I pull out, and you see that was n by 2, I get n tau such factors, so it will be n tau divided by 2 times this term. But what is this term actually? This term, if this picture will now become useful, is an Ising model on a lattice which is n sites along the space direction and n tau sites along the time direction. So it becomes a two-dimensional Ising model with number of sites being n times n tau, such that you have a coupling constant along the space, that's why Ks is delta tau j, and the coupling constant along time is k tau given by this thing, right? And so what we have shown is that the transverse field Ising model is an Ising model on some kind of rectangular lattice, morally a square lattice, with anisotropic couplings. Anisotropic coupling meaning that there is a coupling in space which in general may be different from coupling in the other direction, time direction, but it is a classical two-dimensional Ising model. So this is a really interesting result in that it connects up the statistical mechanics or equilibrium partition function of a one-dimensional quantum system to that of a two-dimensional classical problem with a different set of coupling constants as shown here. Okay. So now to understand what insights we can gain from this realization, if you take n tau going to the thermodynamic limit, you will immediately see that beta, which was n tau times delta tau, remember we're keeping delta tau fixed and small, you will see that I'm going to the zero temperature of the quantum problem. So what does this tell you? This tells you that if I want to, say for example, study some quantum phase transition of a d-dimensional quantum problem, in this case the one-dimensional transverse field Ising model, if I study the two-dimensional classical problem and find some phase transition in the two-dimensional classical problem, in the thermodynamic limit, remember, that will tell me something about the quantum phase transition of the one-dimensional problem. So it offers me this opportunity. Okay, but now there is something bigger we can see. We saw that zero-dimensional quantum problem, which is qubit, was equivalent to a one-dimensional classical problem. Then we went on to see a one-dimensional quantum problem was equivalent to a two-dimensional classical problem. So now we can generalize this. In fact, you can generalize this for not just Ising models, for pretty much all models that we know. The equilibrium state of a d-dimensional quantum system is equivalent to the equilibrium state of a d plus 1 dimensional classical system with a different set of coupling constants. In fact, when you take the classical system to the thermodynamic limit, you will go to the ground state of the quantum system. So if you want to master some of these things that we have discussed today, work out, for example, if I had a two-dimensional quantum Ising model, suppose I define a quantum Ising model on a square lattice, what will be its classical analog? So that will of course be a problem in 3 dimensions. So you'll end up getting something like a cubic lattice, and you can work out the details of that. It's pretty much what we have done, but you have to dash the T's and dot the I's. Okay, it's a good time to summarize what we have done. So quantum many-body systems have different phases with different broken symmetry, etc. Very much like classical systems. So this can happen at 0 temperature. So quantum phase transitions are typically associated with change of entanglement. I have not discussed this in great detail, but that is true. It's worth remembering that. And there is this very interesting connection we found, that equilibrium d quantum system is equivalent to a d plus 1 classical system. That is, I'm repeating, equilibrium state of a d-dimensional quantum system is equivalent to an equilibrium state of a d plus 1 dimensional classical system with different coupling constants. So what this offers is possibility of studying quantum phase transitions in d dimensions by studying classical problems in d plus 1 dimensions and matching coupling constants, etc. Okay, what we will take up next is we will try to actually study the one-dimensional transverse field Ising model in detail. We will make a extensive ground state study of this, and we will use those results to actually infer something about the two-dimensional classical Ising. So I'm sure that you will find all this very exciting. So I look forward to seeing you in the next lecture. Thank you.